Hello everyone, I'm Hajime, and thank you for coming to my talk. I'll be speaking about media mix modeling. So let's get started. This is the agenda for my talk. First, I will explain the background and concept of MMM, and then I will cover data preparation, modeling, and demo with lightweight MMM, and insights and actions. At the end of the talk, I will offer some practical recommendations. For the sake of time, please save your questions until the end. One quick note, if you are interested in learning more about this slide, demo code, reference for this talk, please go to PyData Global schedule page and click my talk. I listed some links. So just a quick introduction. At PyData Global, there are so many famous speakers, but I think most of you don't know me. So let me introduce myself very quickly to explain my motivation behind this talk today. I have close to 5 years of experience in data science, data analytics of marketing, retail, e-commerce area. After I graduated from Kyoto University with a master's in computer science, I worked as a data analyst at Procter & Gamble Japan. Procter & Gamble is well known for its organized marketing strategy. And currently, I am responsible for the e-commerce business of a Japanese clothing brand looking to expand into the US market. Also, I manage and optimize the performance of advertisements at my current company. I believe advertising and marketing is an intriguing topic for PyData audience because every company spends money on advertisement. So today, I want to talk about media mix modeling. So from this presentation, my hope is that you will gain a basic understanding of my key concepts on approaches of media mix modeling. Also, I hope this talk motivates you to try modeling in your environment. First, I'd like to talk about what media mix modeling is. What comes to your mind when you hear the word advertisement? Let me give you some examples. TV commercials are a common approach. Social media ads, like when you check your friends' posts or videos on social media platforms, you probably see many ads. Also, if you Google something, you usually can see some ads at the top of the result. Also, ads on buses, airports, trains, or taxis on buildings, think Times Square, known as OOH, out-of-home advertising, are fairly common. Media optimization has been a challenge for a long time. Some of you might be familiar with the marketing pioneer, John Wanamaker. He supposedly said, "Half the money I spend on advertising is wasted. The trouble is, I don't know which half." A statistical approach for solving this question is called media mix modeling or marketing mix modeling. It is generally referred to as MMM for short. The purpose of MMM is to understand how much each marketing media contributes to sales and how much money should be spent on each. For many decades, companies with huge advertising budget in the beverage, consumer goods, oil, and fashion industry have been working on improving MMM. Also, other tech companies such as Google and Meta have been focusing on MMM actively these days. You might wonder why it is so difficult to measure ROI, or why not just check ROI on the report issued by each media? These are very good questions, but the reality is a little more complicated. The First reason is that the end user has multiple media touchpoints, and the media channel influences are intertwined. Secondly, tracking accuracy is not always correct. Offline media channel influence is hard to track. For example, print media such as newspapers or magazines, we can't track how many people actually see the ads in that form of media. What is worse, even in the digital world, privacy regulations such as GDPR and Apple's IDFA deprecation have been impacting tracking accuracy. Thirdly, randomized experiments, known as a lift test, are impractical. The gold standard for answering a causal question is to perform a randomized experiment by randomly splitting a population into a test group and a control group, where the test group has no advertisements. However, this is not practical because companies prefer not to restrict ad for a long time, as this could lead to lost opportunities. This slide shows the definition and the purpose of MMM. MMM are statistical models which help in quantifying the impact of several marketing inputs on sales. Roughly speaking, there are three goals. The first goal is to understand and measure return on investment, ROI. For example, the model will tell you your ROI on TV last year. The second objective is simulation. For example, with this, you would be able to find out what your sales would be like if more or less money were spent on TV the following year. The third one is optimizing media budget. This step will help you to optimize budget allocation, which will contribute to maximizing sales. This shows the entire MMM steps. The first step is data preparation. The next step is modeling, and then insights and actions. In this talk, I will go over each step in detail. Next, I'd like to cover data preparation. So this is a quick preview of the input data for the MMM model. We use time series data, and we don't use any privacy-related data. As you can see, we have a week, sales, media spending, and other data column. Let me deep dive into what kind of data is needed. The first part is the most important metric, which is the KPI of your business. And this will be a dependent variable. If you are a retailer or a manufacturer, sales is a common choice. However, if you are a mobile app company, the number of apps installed will be the KPI. Next, explanatory variables are potential factors that impact sales. Media data is mandatory because we want to optimize these allocations. And non-media marketing data, such as price, promotion, price and price distribution, affect sales. External factors, such as seasonality, holiday, weather, or macroeconomy data are also important to increase the model accuracy. In this slide, I'm going to talk about the data granularity required for MMM. There are three things that I want to cover. In terms of time, MMMs often require 2 to 3 years of the weekly level data. However, if you don't have that much data, Daily data is also acceptable, but in that case, you will need to be more careful in reviewing the outliers. The next is business granularity. The common approach is to collect brand or business unit level data. For example, Procter & Gamble has Pantene, Head and Shoulders, and Herbal Essence in the haircare category. And each brand team has a different sales, marketing, and media strategy. Make sure to determine the data granularity based on the product line, organization, and decision-making process. When looking at media spending data, a common granularity is the media channel level, such as TV, print, OOH, and digital. But it depends on how much you are spending on each media. For example, if you spend a lot on digital ads, it is better to break down the digital channel into more specific groups such as Google Search Ads, Google Display Ads, YouTube Ads, Facebook Ads, and etc. Because Google Search Ads and YouTube Ads have different funnels and roles. Next, I'll explain the modeling. First, let's start by considering simple modeling. Linear regression on observational data is a common method that has traditionally been used. Here, sales is the objective variable, and media spending factors and control factors are explanatory variables. These coefficients mean the impact on sales. So beta M is the coefficient of the media variables, and beta C is the coefficient of the control variables such as seasonality or price change. The most significant advantage of this method is that everyone can run it very quickly because even Excel has a regression function. Also, it's easy for everyone, including non-tech executives, to understand the results intuitively. However, this method is not grounded in key marketing principles that are widely accepted by the marketing industry. There are two ad principles to consider: saturation and ad stock. Let's first take a look at saturation. The effectiveness of one media channel's advertisements decays as the expenditure increases. Let me say that in a different way. The more money you spend on one media channel advertisement, the less effective it is. This is a saturation point. This is also called the shape effect. The second principle is a carryover effect. The advertising effect on sales may lag behind the initial exposure and extend several weeks because consumers generally remember us for an extended period of time, but they sometimes delay action. There are several reasons why. Consumers don't purchase the items immediately if they already have home stock, or if they plan to purchase expensive items such as a PC, furniture, or TV. They may take several days to several weeks to consider purchasing the items. These examples are what cause the carryover effect. Researchers at Google proposed a method that reflects these two features in 2017. I'll elaborate a bit more in the next slide. The first technique is Hill function. This function will transform media spending through curvature function. There are two parameters here. SM is the shape parameter, which is also referred to as slope, and Km is the half saturation point. As image on the right shows, this function can represent various shapes of the saturation curve by changing these parameters. The second technique is the adstock function, which is useful for representing the carryover effect. The cumulative media effect is a weighted average of media spending in the current week and the previous L-1 week. Here, L is the maximum duration of the carryover effect, and we can use different functional forms for weight function, Wm. A commonly used function is geometric decay, which is the black curve in the chart. Also, if the radical kernel basis function is used for the weight function, the adstock function will be like the red curve in the graph. This curve may work better if the product or media has a large lag due to the delayed consumer response I mentioned above. So let's return to the basic formula here. This is a final model that reflects the carryover effect and ad saturation. The basic approach is the same as the simple model I shared earlier. Cells can be decomposed into baseline cells, media factors, control factors, and white noise. And in this formula, coefficients beta represents the impact of each factor. The target variable is cells per time period. The change here is to apply two transformation functions to the time series of the media spending, saturation and adstock function. Control factors are the other factors that could influence cells, and the epsilon, in this case, is the white noise. So I will go over the demo. Here, let me introduce two great OSS libraries that will help you to try MMM. The first one is lightweight MMM, developed by mainly by Google developers. And the second one is Robin, developed by Meta engineers. Both libraries reflect adstock and saturation functions. The biggest difference is that lightweight MMM is a Python-based library, while Robin is an OR-based library. Lightweight MMM uses NumPy and JAX for probabilistic programming, which makes the modeling process much faster. On top of the standard approach, lightweight MMM offers a hierarchical approach. If you have state level or regional level data, this geo-based hierarchical approach can yield more accurate results. While Robin makes use of Meta's AI library ecosystem. Nevergrad is used for hyperparameter optimization, and Prophet is adapted for handling time series data. I assume that most of today's audience prefer Python, so I'll do a quick demo with lightweight MMM. So before doing the demo, let me just show you the flowchart of lightweight MMM. 1, preparing the data, and 2, training the model, diagnose the model, get an optimized budget recommendation, and save and load model. So let's do. So I'm going to use Google Cloud to show you the demo. Just as a reminder, if you want to download my demo code, please go to my PyData Global schedule page and click my talk. And my code is based on the sample script that is available on lightweight MMM repository on GitHub. First, let's install the lightweight MMM library using pap command. It should take about 1 to 2 minutes. If you get the error restart runtime, you need to click the restart runtime button. Also, let's import some libraries such as JAX, NumPy, and necessary modules from the lightweight MMM. Next, let's prepare the data. The official sample script uses a simulated dataset that is generated by the library's function to create dummy data. However, I'm going to use more realistic data in this session. I found a good dataset on a GitHub repository, Sibylle MMM stan. I'm not sure whether this dataset is real, dummy, or simulated data, but for me, it looks more realistic than any other data I found on the internet. Let's take a quick look at it. This data contains 4 years of records of data at a weekly level. For simplicity, I use 7 media channels for media spending data and holiday and seasonal information for control variables. Next, I'm going to pre-process the data. We split the dataset into train and test. I'm leaving only the last 24 weeks for testing in this case. Also, this library provides a custom scaling function for pre-processing. In this demo, we divide the media spending data, extra features data, and the target data by their mean to ensure that the result has a mean of 1. This allows the model to be agnostic to the scale of the inputs. The next is training. We can choose an add-stock function for the modeling from 3 options: hill add-stock, add-stock, and carryover. It is generally recommended to compare all 3 approaches and use the approach that works the best. And then execute the modeling using the fit function. Training takes about 20 minutes, depending on your environment. Once training is finished, you can check the summary of your trace. The important point here is to check whether all hat values for all parameters are less than 1.1. This is a checkpoint when you run Bayesian modeling. Also, we can visualize the posterior distributions of the media effects. And this is optional, but you can visualize the prior and posterior distributions for every model parameter at once. Now, let's do a fitting check. Your model's fit to the training data can also be checked by using plot model fit function. R squared and MAPE, mean absolute percentage error, are shown in the chart. In this example, R squared is 0.9 and MAPE is 23%. For our next step, I'll do a fitting check using the test dataset. Generally speaking, R squared is considered good if it is more than 0.8. Also, for MAPE, the goal is for it to be 20% or below. And this is the visualization of the prediction result. R squared here is 0.62, and MAPE is 23%. Honestly, the R squared and MAPE values here are not ideal. However, I do not have any additional data, and I'm not even sure whether this dataset is real or a dummy. That said, I'm still going to be using this dataset and modeling to show you the insights. I'll be going over how to improve the model in more details later in this talk. Now I'm going to go back to the slide to explain the outcome and insights. We can quickly visualize the estimated media and baseline contribution over time by using this function. This graph shows that about 70% of sales are baseline sales, which is represented by the blue area. The other colors shows media contribution to the remaining sales. This graph shows the estimated ROI of each media channel. Each bar represents how efficient the ROI of the media is. In this case, TV and online display media are more efficient than other media. Looking at the result, overall, these companies' marketing activities work quite well. With this command, we can visualize the optimized media budget allocation. The graph shows the previous budget allocation and optimized budget allocation. In this case, direct mail and radio should be reduced, and other media should be increased. Summary. So, is MMM practical? I think so. If John Wanamaker were alive today, I would advise him for the following. You should try MMM. However, a tailor-made model is needed for better insights and actions because there is no one-size-fits-all model, as every business is in a different situation. Then, how do we improve model accuracy for better insights and actions? First of all, better data is important. You need to choose the control variables carefully that affect your sales based on your business. Google researchers identified that search volume for relevant queries can be used in MMM to control the impact of paid search as appropriate. If you spend a lot on a specific media channel, it is better to break down the media channel into more specific groups. The next recommendation is to improve the modeling. Of course, hyperparameter tuning is important. In addition to that, trying the geo-level hierarchical approach is a good way to get better accuracy. The third recommendation is to work with your marketing team and do actual experiments, known as a lift test. As previously mentioned, it is unrealistic to do randomized experiments in all media. However, experimentation at key points is useful to get the ground truth to improve the model. Meta recently released the GeoLift, which is an OSS solution that can be useful for geo-based experimentation. So this is a summary of my talk. So I explained about the MMM, and I explained the concept of saturation and ad hoc function. If you are familiar with Python, lightweight MMM is a good first step. So this is the reference of the talk. And thank you for your time. If you have any questions or comments, please feel free to contact me. So thank you very much.
Oh, and definitely thank you. We have a couple of seconds. We're still waiting on the next speaker to show up. I've got, oh, there she is, but still. Wonderful talk, Hajime. Thank you so much. One of the most detailed and application-oriented M talks I've listened to. And someone, Mark Warren asked, have you tried Robin?
Robin? Yes, I tried Robin, and Robin is released 2 to 3 years ago, so it offers a lot of options. And in terms of algorithm, Robin is a little bit different from lightweight MMM, but maybe you have time. I think both Robin and lightweight MMM are good libraries, so maybe you have time. Trying both solutions might be good.